All right, welcome to the second colloquium of the spring 2023 semester. So you may recognize our speaker today, Dr. Ettore Vitali, okay, our newest and most energetic faculty member. So I'll do a brief overview of his academic sort of trajectory. So he got his PhD in astrophysics and applied physics at the University of Milano. Then he did several postdocs. He did a postdoc in Trieste, another postdoc in Milano, and last he did a postdoc in Virginia at the College of William & Mary before we were lucky enough to convince him to come here and join the faculty in 2018. He's won several awards since he's been here. He won the Extraordinary Teaching and Extraordinary Times Award from the Provost. It's like an award for like, hey, you did a good job teaching during COVID. You did a fantastic job. He also won the Provost prestigious Promising New Faculty Award, which is like one of the top awards within the university. He's recently published some of his research in Physical Review Letters, which is the top journal in the field. And he also, within the past 6 months or so, found out he was awarded a large NSF grant to continue it or to further his research. So today, Dr. Vitali is going to tell us about quantum mechanics and a world of infinite possibilities. Let's welcome Dr. Vitali.
Hey everybody, welcome. Very happy to see good participation today. Even more happy to see many of my students, or the students in the university. Very happy to see my colleagues as well. Well, and also thank you, Doug, for choosing this nice image of the on the flyer. That was not my choice, but I think it's a good. It would be a good starting point. So let me get. Well, Doug already introduced me, so thanks a lot. And I think I know at least 90% of the people I see. So if anyone wishes to know me more at the end, I will be happy to discuss more. So let me just go straight in. And essentially, we are just a few years from a huge anniversary in physics. Because in 1927, really an equation which changed the history of physics was written down. And it was written down by this scientist with a pretty complicated name, but most of us just remember Schrödinger, the last name. He lived like across the previous century. And essentially what he wrote down opened a new path for physics. Because that was a very very vibrant period for physics. And my apologies for the pretty low quality and actually pretty even inaccuracy of this, but I found it online and thought it was useful for a pedagogical point of view. Because what came clear at the beginning of the 20th century is that what has been very well established for many years, or actually for many centuries, which is Newtonian mechanics, comes into difficulties when either we go to very fast system, and that happened a few years earlier than this, or we go to very small system, and then later on people build and try to combine the two things. The reason why I'm saying this is not as accurate as I would like it to is that actually relativistic mechanics should go up also on the size axis. Because when we are studying something very, very big, we do need relativity. That is well known. But today I'm just exploring this transition. Because when you get into the atomic scale, apparently Newton's laws do not hold anymore. And we need to write something new. And that something new was written in 1927. It may look like a very complicated abstract equation. We will not look too much into the details of the equation itself, but its publication was really the paradigm shift. But you can simply look at it as the quantum version of what Newton's second law is. Because if you think Newton's second law is an information that if you know all the forces acting on the system, you can predict the trajectories. Schrödinger equation is an equation that allows you, once you know all the forces which are encoded in this mathematical object called the Hamiltonian, then you can predict what the system is up to. And we are now basically a century later. In 4 years it will be a century. The amount of experimental confirmations is unbeatable. We had really billions or certainly millions of experiments which did not falsify quantum physics. We have several applications, and you don't need to look far. This laptop, all your smartphones, none of those would be understandable or usable without the laws of quantum mechanics. And essentially, there are several fields of physics that wouldn't even exist without quantum mechanics. From atomic physics, and those two are like, my research field is at the intersection between those two. Condensed matter is most likely the biggest field in physics, strongly related to chemistry. Quantum field theory would be the theoretical evolution on the path of quantum physics. It's well known that we wouldn't understand the evolution and the nature of many stars if we didn't postulate that the world behaved in a quantum way. And on more of the application side, material science nowadays is huge. So for any of you is thinking about maybe jobs in the future, all those fields might be very fertile fields for you to look into. And in terms of the perspectives, quantum computing and quantum technology are really coming forward as a sort of the new path of technology. And many scientists are convinced that this century will be remembered as the century of quantum technology. Don't know if that is true or not. That is prediction of the future. And also biomedical science is making progress every day. And it entirely relies on quantum physics. So it's not just sort of something on the side, something only for theories. It really appears to be a cornerstone of our knowledge of science. Now, just to speak a little bit about myself, so since 2018 I started developing this computational quantum physics research group. And nowadays I'm very happy to be at Fresno State. Those are my funding people. NSF gives me money, Exceed Access gives me CPU time on their supercomputers to run my calculations. And if I want to summarize in just one sentence what we do is, the idea is to use the most powerful computers that we have right now to see if they can help us predict properties of quantum systems. And my typical investigations are in the realm of superconductivity. Well, Don is an expert of this experiment, so please ask him if you want to know more. Superfluidity, which among their features there is this pretty spectacular ability to climb the walls of a container and go down. So if you want to take a glass, put it in a superfluid, bring it up. Apart from the fact that you would freeze your hand to death. But if you were able to do, the superfluid would gently climb the wall of the glass and go back to the container where it's coming from. And there are strong indications that the same physics would dictate the behavior of some of the most mysterious systems in the universe, like neutron stars or somewhere in the interior of them. Now, if you want to think it in math terms, I put it very small here. This is still Schrödinger equation, but all my job is dealing with that equation. In my field, we don't challenge it. That will be other branches of physics. Essentially, what I do is look into that equation in different situations and see what can I understand about physics. I have quite a few collaborations. The current one are with Simons Foundation, that's my most important in New York, Sherbrooke University, I forgot the name, sorry, with Sherbrooke people, UC Davis, Rice University, and in Italy, University of Milan, where I did my PhD. I was very happy to meet a huge group of motivated students here. Some of those are in this room. If I forgot a name, very sorry about that. Just please remind me as soon as I thought I put them all, but I'm not entirely sure. And so I had Patrick was the very first student. He reached out to me even before I came here, and I'm very happy that most of them are now in prestigious PhD places, just fostering their career, their future career. I'm particularly happy that so far the group, since 2018, we have 10 publications in peer-reviewed articles, a total of 42 presentations, and the most beautiful thing for me is that I didn't need to do 22 of them, so that would be very stressful. But in particular, I had my students presenting 22 times in the last 5 years, and I'm particularly happy with that. And it's interesting, so we will have 2 students present at the Merck meeting in a couple of weeks, and so on. So what exactly do we do? Well, the most part of our energy in the group is dedicated to predictions about quantum systems. So we take a particular Hamiltonian, we start from a given collection of particles, given model for the forces, and we try to understand, are we dealing with a metal or an insulator? Are we dealing with some interesting magnetic phase? Are we dealing with some rotational, some breaking of rotational symmetry? Are we dealing with topological physics, exotic phases, and so on? Or are we dealing with superfluids and superconductors and many, many other things? What are the modes? And I dedicated quite a few colloquia in the past to discuss topics of this form. But we have like a physics part of our investigation, and then we have a more methodological part where we try to see if we can improve our algorithms and maybe take advantage of artificial intelligence, which is so fashionable nowadays, to see if we can advance the knowledge in these fields. But this is only one page of what we do. The other one is more philosophical, so something in the middle between physics, teaching of physics, and understanding of physics. Because quantum mechanics is challenging. So what does it exactly mean? And that's part of what I would like to share with you and essentially discuss with you in this colloquium. Can we do something to optimize the teaching of it? How about using computers to generate visual support to the teaching of quantum physics? But in particular, and this is the topic of my talk today, what does quantum physics tell us about the universe we are sitting in? Is there any, if we just follow the flow of the theory, read Schrödinger equation, follow it, are we going to find something which makes sense? Or may we find something that challenges our understanding? And that's what indeed happens, and that's what I would like to discuss today. So I am in plenty of wonderful discussion with my students. I noticed Soban is here. Soban was one of the students who asked me the maximum number of questions about similar topics. I'm grateful for that. So my plan for today is to sort of try to give you a glimpse, some ideas about what the main questions are. And I'm giving you questions, I'm not giving you answers. Because in my opinion, that's the scientific mindset. Very few answers, many, many questions, enjoy the process. That would be my recommendation. But before that, I need a little bit of notation and just naming convention, just to make sure we are on the same page. I will try to keep it as simple as I can. So let us put in the mindset of a scientist. We are facing a physical system and we want to study it. If we want to develop a theory, we essentially need 3 ingredients. The first is, how can I characterize what the system is doing? That is what we typically call the state of the system. What are the degrees of freedom that we are considering? This is what we call the state. Second one, since we are scientists, what can we measure about the system? This is what we call physical observables. The third one is what happens if I let the system alone and let it go. The system will evolve as a function of time. So essentially, those 3 ingredients are the ones that we need to address if we want to design a theory about a system, a phenomenon, or something. And both classical physics and quantum physics, they both follow that paradigm. But they give very different answers to those 3 questions. So just a quick reminder, and we'll go fast here, because that will be probably physics 4A. What is the state of a classical system? Essentially, positions and velocities of all the particles involved. If I know that, I know everything. What are observables? Functions, aren't they? If I want to measure the energy of the system, that's 1/2 mv squared plus whatever potential energy I need. So if I know the state, I just apply a mathematical function, and I get the observer. I have one state, one value for the observer. If the state changes, the observable may or may not change. What about the time evolution? Well, here I go even faster. I hope all of you remember this. This is celebrated Newton's second law. I hope I didn't put a mistake in there. No, I didn't. Because that would be a very bad start. But the point of Newtonian mechanics is, if you tell me what are the forces acting on your system and inside your system, then I can predict where the system will go, and in principle, even when the system was before I started observing, provided that I have a way to know where the system is now, or where the system was at a given initial time that I choose. Okay, any confusion about this? This is classical paradigm. Now what? How does this change?
Okay, everything.
Essentially everything.
Yeah.
First of all, what we call state of the system, frequently called a wave function. Well, this is a mathematically interesting architecture. It's a vector in a Hilbert space. I can just, if some of you is not comfortable with vector in a Hilbert space, just think of a set of numbers, set of complex numbers, there for us, and enough to characterize what the system is doing. And, well, when I have the classical state, I want to measure something, I compute the value of a function. In quantum physics, when I want to measure something, I apply an operator to the state. It cannot be a function because a function doesn't mean anything in a vector. Well, no, operator is a function indeed. It's the vector space function version of what we call functions in a normal lab. So let us continue a little bit. I told you, a state is a mathematical object. Observables are operators. And this is a particularly new thing, that given a state, where in general, any operator has a set of eigenvalues. Those of you who are familiar with linear algebra certainly know it. In general, it's just a set of numbers that somehow correspond to the operator. And physically, the meaning of those are the possible values of my observable. If I'm trying to measuring a quantum property, I have an operator, the operator has a set of eigenvalues. Those are all and the only possible values of the quantity. And the key point of quantum is that if I have the state, in classical physics, if I have the state, I apply a function, I know the observer. In quantum physics, if I have a state, I don't know the value. I only know the probability to observe any of those values. And you can compute it as that architecture, like projecting the state onto the eigenstates, but don't worry too much about that. The key point for me is that you have observables, but quantum observables come with a huge amount of potential possible values. And if I know the state, which is the most I can know about the system, I don't know what is the value of the quantity. I have many, many, many. I call it the world of infinite possibilities. Sometimes they are finite. There are situations in which it's just one. But most of the times I really have many, many, many possibilities. Now there is a common doubt here that I invite you as students to keep you in mind that every time you visit a new formalism, sometimes you discover that you're just rewriting what you had before, only in a more complicated way. Well, there is clear evidence that this is not the case here. And the crucial point is this nature, is this intrinsic difference that in classical physics, you know the state, one and only one value of the quantity. In quantum physics, you know the state, you have a probability distribution for the values of the quantities. And that is a difference that you cannot reconcile, at least nobody was able to reconcile yet, using any reformulation and mathematics. And it has been almost a century. So just to go ahead, this is perhaps the most obscure postulate of quantum physics.
Right.
Because very few people know what does this mean. But quantum information people are verifying this every day. And as you will see in a few minutes, it has huge implications in terms of what we understand. And the key point is that every time we make a measurement on the system, as I told you, we will find one of those possible values. But then in classical physics, when you measure something, the state doesn't change. You just measure, but the state continues on its own. In quantum physics, as soon as you measure, you dramatically change what the system is doing. And this is normally written like this. So what the state before collapses into the projection of the state on that particular subspace of your full space. In that sense, like I measured the first time, I got a value. If I keep measuring without re-preparing the system, from that moment on, I will keep getting always the same value. I remember my master thesis advisor hated this postulate. He never thought about it, but it's there. And as you will see, it's pretty relevant. Conceptually and intellectually very strange, because you see that we make a postulate without any description of the actual measurement process. So it doesn't matter how I measure it. I just measure somehow, and something dramatic happens to the system.
Well, that word observable, that's pretty
yeah.
big. Yeah.
Well, observable.
Is it observable?
So last thing that I tell you, remember my three items, the state, the observables, and the time evolution. Well, the time evolution is given by Schrödinger equation, provided that I do not take any measurement in the midway. Because as soon as I measure, I make a disaster in the system. Okay, yes please.
What do you mean by the word evolution in time? Like, what do you define evolution in this context? It just.
Oh, evolution just means that the system changes in time.
So you're just using.
It's nothing related to a bio. Well.
No, I wasn't doing it. It's just that word keeps changing.
Evolution means just the state changes. Like my position, as time flows, I keep changing position. The time evolution of my position.
All right, thank you so much. Sorry.
You're very welcome. No, please. Yes, please.
Notice that in the physical and the biological sciences, we use the word evolution slightly different. In physics and in astrophysics, evolution means change to one system, whereas in biology, Darwin's original theory of evolution by natural selection, it meant change to a population of systems.
Yeah. Definitely, this is just change.
Thank you.
Remember, the state is what we know the system is doing. Now, in 10 seconds, whatever system I'm studying will be in a different state. That's the time evolution.
Thank you so much.
It's the most common terminology that we use.
But not any changing, driven by your Hamiltonian.
Well, that would be Schrödinger equation, definitely. If I take a measurement on the system.
Because biological evolution is not Schrödinger equation.
No.
And thermodynamic evolution also, it's not Schrödinger, it's different. So that's why it's a confusion from pedagogical point of view. So we are strictly oriented to this rule. You have Schrödinger evolution.
Yeah, we can go there. that would be an interesting discussion.
No, sorry.
No, that's fine. And yeah, I would have a lot to say about that, but that wouldn't be the direction where I could dedicate an entire talk to that.
Yes.
But that would be a little. No, that's a very good question, because that might have created some confusion. But let me put it like this. If the system evolves on its own, under the action of the internal forces, those forces are encoded, and maybe some external field that acts like gravity and electric field. In that case, the evolution is entirely driven by the Hamiltonian and is given by Schrödinger equation. But be careful. As soon as I take a measurement, something changes.
Yeah.
Now, from now on, so this is all I needed from the theoretical point of view. Now, those are all the postulates. So this is our theory. Let us ask ourselves this question. If we follow this postulate and bring them into the way we look at the universe, what are they telling us? Are we safe with those postulates? What are they predicting? And the first notion that I would like to explore It goes under the name of realism. I will define the term because this can be even more confusing than evolution. I certainly understand that. But what I mean by realism in this context is that the measurement outcomes are determined by properties of the system prior to and independent of the measurement process. Let me try to paraphrase it a little bit. I'm telling you that if Doug is doing his own thing and I want to measure his velocity is already there, whether I measure it or not. There is no way my measuring his velocity is disturbing him, changing him. Okay? Maybe. Well, it depends. If to measure his velocity, I put my leg in his way, he rushes on the ground. That can be a similar step. By the way, this was one of the points on which Einstein insisted a lot. There is a very famous quote by Einstein who said that, do you really believe that the moon is not there when you're not looking at it? But
how did you know?
But remember, let us try to be scientists in the sense that we don't have our common sense disturb us now. We follow the postulates of quantum theory and see where it brings us. So how do we analyze the thing? Well, I could discuss any quantum system and set up the discussion, but perhaps the simplest and maybe one of the most interesting is the celebrated qubit. How many of you heard about this term? Almost everybody. Qubit is the simplest quantum system that you can imagine. It's actually like a template of a quantum system. So there are many, many realizations of what we call a qubit. It's not just like a particle on a spring. You can have organic ones, you can have superconducting ones, and so on. For me, a qubit is simply a system which has just two physically distinguishable states, which, according to quantum physics, means that the entirely general state of a quantum system is just summarized in two numbers. And not even because they are constrained by normalization. Essentially three numbers. But that doesn't really matter. Just for your personal visualization, this is perhaps the simplest way of thinking of one particle, which can be a rotating. You choose an axis, say z. The particle can be rotated clockwise or counterclockwise. Imagine those as your two states. Now, what's interesting about that? Well, first of all, let us reproduce all the key ingredients I was mentioning. What is the state of a qubit? So how do I know what the qubit is up to? I just need to know those two numbers. Which component on 0 and which component on 1. What can I measure on the qubit? Remember, second item, measurements. Well, on the qubit, what I can measure in the simplest way are all of the angular momenta. Imagine just as up or down, like clockwise or counterclockwise, but I can have three Cartesian axes. I will not do because I spilled coffee all over the room, but if I had a ball I would do. But I can have a particle rotating like this, or I can have a particle rotating. So I can measure imagine to measuring the sign of the angular momentum around the three axes. So those of you who met Pauli matrices, just welcome them. If not, this would be the mathematical version of the operators. And those of you who are really precise on units, you might notice I left some units out. Please forgive me for that. I just wanted not to overcrowd the class. Okay, so what's here? And well, the reference is, this is called the basis, but those two special states refer to two situations where, chosen an axis z, say vertical in the page here, I have either clockwise or counterclockwise. So if you might remember from some, but it doesn't really matter. Now, just to fix a precise example, a very famous state. Imagine we have a source somehow, somewhere, that prepares a qubit, so this simplest quantum system. And imagine this is the state. Very famous state. Let us take a measurement. Well, if we take a measurement, and we measure the spin along x, we would discover that every time we make the measurement, we find the value 1. For those of you who like math, this is simply because this is an eigenvector of that particular operator with eigenvalue 1. So apparently nothing strange here. And what I find this kind of clause pretty interesting because what you have if you do a mixture of those two, essentially you get something. Although you can try to grasp intellectually what that means, but essentially
A mixture of those two, I don't know.
So no violation of realism yet. You agree? In this sense, I take the measurement, I find 1. Why? Because it's an eigenvector. So nothing strange yet. But let us change point of view. Let us measure the spin along z. If I measure the spin along z, before the measurement, I have exactly 50% chance of finding it like this, and 50% like this. By this I'm telling you that according to quantum physics, remember I'm not throwing in my opinion here, I'm just following the flow of quantum physics. When I'm dealing with the quantum system, before I take the measurement, the value of that quantity is not the one. That is against what we call realism. Before we look at the moon might be there or not. That Einstein didn't like this. And I'm not giving you my opinion here, I'm just following what the postulates of the theory are telling us. So I'm being very, like a surgeon, very just following, and we will see something way weirder than this. So if you have this state, and you take a measurement, so this is just another representation. Imagine we take a measurement. Later on you will have a collapse, because that's what collapse means. And after that, I will keep finding +1, +1, +1. So yeah, I have those two situations. Both realities exist at the same time. The cat is... Well, it's very risky to put too much intuition there. That's what the math is telling me. But the two possibilities are there together. After I measure, one possibility disappears. Possibility though. I'm not telling you that it's a mixture of... It's not like a, I don't know, like a ball where like dices are rolling, because those have values. I don't know them yet, but they have values. This
you apply a magnetic field, you will just go one.
What's that?
You collapse means you apply a magnetic field because you apply something reliant.
If you follow the postulate though, any way you make that measurement, you will induce that collapse. That's what we theorists don't like about that postulate. Because we would like to have a theory about the experimental phenomenon that induces the collapse and how does the collapse happen. While the postulates are telling us, well, as soon as I measure, no matter how I measure it, I might take a hammer and destroy it and get a value. I might do the super sophisticated, as soon as I measure, it's collapse. For many years, physicists thought that it was mostly like a mathematical thing. But now quantum information people are seeing those states on a very so they really see the states in practice, and they are seeing this collapse all the time. So there is something deep there, something we don't understand yet. Okay. Now, let's get weirder and weirder. What do we mean by locality? Well, the phrasing may be a little bit hard, but so what I'm telling you is that the outcome of a measurement in a region A is not affected by a space-like separated event happening in the region B. Let me put it very simple. Doug is doing something there. I am doing something here. If we do it exactly at the same moment, there is no way that everything I do can have anything to do with what he does. The reason is that at least light should have time to go there for some exchange of information to happen. Makes sense? More, because between me and Doug it's very hard to have such, because light will not take that long to go from me to Doug. But what they typically do is that they have a source generating photons. Those go almost at the speed of light, or at the speed of light, and they send photons in opposite direction. And they have two labs, say one in the US, one in Japan. And they have one scientist per lab. They look at the two photons. The locality idea is that if they measure at the same time. No way the information on one side can have anything to do with the information on the other side. So essentially, well, this is a very fancy representation. Those will be my two scientists for a typical reason called Alice and Bob, because all the texts about quantum information call them Alice and Bob. And the idea is that in the classical world, imagine Alice and Bob receive two packages and they say, well, we know they will contain a chair. It can be either red or blue, which is the typical situation of.
So this is Schrödinger's cat with a cherry. No?
Well, this is classical though.
Okay.
What I'm saying is that if they open at the same time, there is no way that there is any correlation between the two results. And also that the chair was certainly already blue and this was already black. They just opened. But that's not what quantum physics tells us. Because my classical mind, I challenge you to challenge what I'm going to write, will say, well, the chairs were definitely blue and red before the boxes were open. Would you contradict that?
Yeah,
So do you think that when the company makes the chair, I have like a rainbow in the, inside, the chair keeps changing color, and when I open the... So that is what seems. Also, is there a way that my actual opening of the chair can change the color of the chair? Well, unless I open with a spray in my hand, but that would be a different thing. And also, do you agree that if Alice finds a blue, if they measure at the same time, what I find cannot influence what somebody else is finding. If we measure at the same time. If we measure at different times, maybe there is some time to call the company, say, please mail him another color, and that's another story. So what about our qubits? Well, this is not just a 1 qubit story, it's a 2 qubit story. Okay? We need 2 of them. Now, this is the super famous Bell state. Here I have 2 of my, you can consider them rotating balls or caps or whatever. So I have this situation here. Classically, that state means nothing at all. Quantum mechanically, that is a perfectly well defined. It's just a state, isn't it? It's a vector. So nobody would say that that is an illegal state. This is perfectly well defined. It's called an entangled state. Because you see that we don't know if they will rotate like this or like this. But we sort of know that they rotate the same way. You see that there is one where both are like this, and one where both are like this. There is nothing like this. And that's the entanglement. But, so, let us do the experiment. Imagine we have a source, and we have math. Then another problem would be how to realize that, and they did realize this. There are plenty of experiments that did this. We have a source, it prepares our 2 qubits in that particular state. Now we find a way to send 1 qubit to, imagine Alice, and 1 qubit to Bob, or 1 to Doug and 1 to me. And we are very far. The easiest way to imagine this is, imagine I have a source of photon, a source of electromagnetic waves. I prepare 2 photons whose polarization are correlated, and I send them 2 photons like this. Then they travel for miles and miles and miles, and there are 2 scientists. I am here, I get the photon passing by, and I have all my detectors here. Doug is there with all his photons close to his coffee and so on. And we had agreed before that we had synchronized our clocks and say, okay, we cannot speak in the middle, because if I call him in the meanwhile, the photon will be long. The photon goes fast. But we had decided that we have our clocks synchronized, and when the clock ticks, I press the button and measure if it's doing like this or if it's doing like this. What will we find? Now, the first thing is, let us imagine that they decide to measure at the same time. Before it was opening a box, now it would be more realistic to use a microscope, but anyway, this is just for fun. So say they agree about measuring the same quantity, say the z component of the spin. Well, if they do that, they will find always the same, do you agree? Because what happens is that as soon as Alice's Alice measures, the wave function will collapse. So say Alice finds +1. This wave function will collapse, and will collapse in 0, 0. So there is no way Bob can find anything else. So this is already pretty weird, but not that weird. We will do more in a moment. Why do I say that? Well, the example that I keep in mind is sort of like this. Imagine I have like a pair of red socks, and I fly somewhere, but I forget one of the two at home. But I know they are both red. So when I say I get to Japan, I open my luggage, I see just one red sock. I know that my wife in Fresno will see the other red sock, and I know she will know it's red, just because they were red before. So the fact that they will measure the same thing, even if they can speak, that's not that. There might be something to that, so we can sort of save this. But the point is, they can measure also something else, and that gets way weirder. Because now what? Well, this comment was just about my red socks, so we can skip this. Imagine they now decide to measure another one. Because they see a photon, they are not forced to measure along this axis. They say, well, let us look at how the particle rotates around this axis. And homework for the students who are interested, prove this one. You will discover that, and this is an identity, this is math, and nobody can contradict that, that if you write the state like this, you can actually write exactly the same state, also like this. It's like a 10-minute, not even, 5-10 minutes linear algebra exercise. What I'm telling you is that this state is the same as this state. That is very weird. Because it's a different motion, isn't it? So now, so essentially, all the considerations that apply to this essentially apply to this. It's the same state. So there is something even more mysterious here. Because what happens now? It happens that if Alice measures the x component and say finds 1, also Bob must find 1. That is just following the postulate. And say, well, isn't it the same story? No, if we put the two things together. Because how can Doug know what am I going to measure? But do you agree that depending on the choice that I make, he will find a completely different physics? Because before, say I measure the z component, I find +1. There is no way he can find -1. But now I measure the x component, I find +1. But he can still measure the z. And now he has 50% to get +1 and 50% to get -1. So depending on what I do, he can or can't get some values. That's no classical. There is no classical correspondent to it. Does it make some sense?
Yep, Einstein didn't like that either.
So I know Don is following very carefully. He's struggling, but then, okay. So just this summary. You can think of Alice and Bob or myself and Doug, whoever you prefer. The idea is that if Alice measures the z component, then say Alice finds +1, then the wave function collapses. So for Bob, the z component must be 1, but the x component would be undetermined. So you can find both values for the x component. Right, so I try to use a color code to distinguish between x and z.
Yeah, that's good.
Now, vice versa. Alice measures the x. So Bob is constrained on the x. He can only find +1. But the z can be plus or minus 1. Yes, please.
So this is like the first time we've been like going to quantum more. You're using a Cartesian plane, right? With like an x and y axis, with the z is the.
Doesn't really matter, but you can choose any. Normally, in a normal lab, the z would point toward the series,
Okay.
and the x and y would be on the floor. But nothing changes here. If somebody is getting an headache, my apologies for that. Just sit down, sit and enjoy. We can discuss it later. But what is the reflection? just to summarize in one word, is that we can call it polarization, angular momentum. Normally those are photons, so we speak about polarization, but it's essentially the same thing. The polarization of both particles is influenced by the measurement Alice performs on their subsystem. And this is not a local thing. Locality is violated. But let us make it even just one step worse. You remember some special relativity. You know that simultaneity is not an absolute concept. So we can go to a reference frame where Alice measures after Bob. So something that happens later will change what Bob will find earlier. Is that even possible? I'm throwing questions, not answers.
It seems that if Alice and Bob are both sitting still with respect to each other, you might want to prefer their reference frame.
Good question.
They're
Good
wrong.
observation. It's,
What if they're moving with
somebody
respect to
thinks
each
like
other?
that.
Yeah, you gotta get relativity, sure.
That's a very good, I really like that observation.
You're considering the simplest case, so they're both at rest compared to each other, right? That's how you started.
So the last thing I want to discuss today before saying hi to you is a little bit of a more, like, sort of a more practical view of the more mathematical, something that we can rely on number when we, because somebody feels, well, what you just said might be interesting, but isn't it possible that maybe just with your words you are creating some, so can we make it mathematical? Yeah, we definitely can. So let me show you how. So imagine we just go back to classical. We have just balls which can rotate. So imagine I have a source that generates two balls, say 2 billiard balls, and we will keep observing how they move. And they said one to Bob and one to Alice. Classical though. And as I've been done before, Alice can measure two different observables, like rotation along this axis and along the, and like this. And Bob can do his own thing. No strict regulation that those must be the same. They can. Just for simplicity, assume that each measurement can yield only just +1 or -1, because otherwise we make everything uselessly more complicated. Now, they don't speak to each other apart from the fact that they measure at the same time. I say I am Alice, I choose whatever, Doug choose whatever. So we don't know, he doesn't know what I will going to measure, I don't know what he is going to measure. Okay? But it's classical. So you agree with me that whatever we decide to measure, those quantities are already well defined in the balls before we measure them. That's classical, isn't it? So just to make a concrete, precise situation, like imagine that the ball already has those three values, like, I don't know, like one of the ball. So A1 is what Alice will measure on the, those are the two options for Alice, those are the two options for Bob. There are two balls, one goes to Alice, one goes to Bob. And imagine that the two that goes to Alice have 1 as a result of both measurements. And there is it's just one example. So you agree that whatever they will do, this is a table of the possible results. So I got my ball, Doug got his ball. I can decide to measure A1 and get 1. Doug might decide to measure B1 and get 1. Because those are already in the particle, it doesn't matter what we do, we just detect them. Or I can measure A1, Doug can measure A2, or I can measure A2, Doug, and so on. Now, if we mix together all those numbers, constructing like an algebraic manipulation of them, you will discover that the value of this is 2. Why would we care? I will reply in a second. Now, what you can show that is that whatever initial values the source can generate, as long as they are either plus or minus 1, if you combine 4 numbers with values plus or minus 1 in that particular algebraic form, you can just get plus or minus 2. That's elementary arithmetic or algebra, no more than that. So I have actually 16, like a few possibilities, like 1, essentially for each of the 4 I have 2, so to the power 4. And, but in all cases I get either +2 or -2. Okay? So if we don't know what the source is doing, because before we measure, it's true that the measurements are there, but we need to do the measurement to know. So imagine that we average over all the possible values that the source might have generated. So imagine the source is somehow random. Still classical, but we don't know what ball, how a ball will come out of it. But you agree with me that if we compute something that can be either +2 or -2, the average cannot be bigger than 2. Because I try one, you get 2. I try another one, you get -2. No way the average can be bigger than the maximum of the values of a random quantity. That's another like very basic math thing. But you agree that this condition must hold under the classical assumptions. And the classical assumptions are that Dag and I do not affect each other. And that seems the only option because we measure at the same time. And the physical properties are already in the ball, whether we measure them or not. So Dag is still sitting down even if I move out of the room. Maybe I don't know, but presumably he's still sitting down. Okay. Now, what happens if I go back to my state? Now, I prepare my 2 qubits. This is the state. I send one of them to Bob, one of them to Alice. This is a pictorial representation that I found online. And you say, well, just for the math of the exercise, Alice can measure the angular momentum with respect to z or with respect to x, while Dag is more sophisticated than me, so he wants to measure around the diagonal. But this is just to clean up them, just for the purpose of the math. So don't worry about that. He's still taking 2 measurements. So all those are we just change. Imagine we have a detector with different axes, and we just look at and how the particle spins. Well, let us do exactly the same thing we try to do classically. Let us take those measurements, combine them in the same way. Now, we can do the quantum, following the postulates, we can do the quantum expectation value. What you discover is that if you do the quantum expectation value, you find 2 times square root of 2. Bigger than 2, isn't it? So, what I told you, that this is exactly the same thing that I told you before, but in a mathematically, in a numerically more precise way. So what am I telling you? I'm telling you is that if I assume that realism and locality are true, and I try to describe this experiment with sources, I must find a value which cannot be over 2. If I do the quantum calculation on the entangled state, I do exactly the same thing. I follow exactly the same procedure. I just trust the postulates of quantum physics. I find 2 times square root of 2. Now, interestingly, it has been probably 50 years. There has been, as far as I know, 15 or 16 experimental attempts to reproduce that experiment. Many, many times people found values bigger than 2. No value bigger than 2 times square root of 2 have never been observed. Interesting, isn't it? Yeah, so it sounds like there is something pretty deep in quantum physics, because it reproduces the experiment at a level which was never possible before. It makes our computer work. It makes our smartphones work. And what does it mean? Because such simple consideration, why? This table is still here and is still steady if I don't look at that. Or, if Dag and I do things exactly at the same time, so to the point where, according to special relativity, I might do something later than him, but still what I do later seems to have statistical correlation with what he does. So here we have three things. How do we take? What's the take-home message of that? Well, this is an open, big question. Most of the scientists are now challenging, are trying to save locality, but challenge realism. Because they say, well, because locality seems really very, very hard to challenge. Why somehow we come to grips with this idea of like the measurement not being completely defined before we make the work. And then there are attempts to conciliate the two. Then there are all a spectrum of ideas that typically go under the name of hidden variables theories. So the idea is that there is something deeper, something that is not accessible to measurement, but it's actually acting. But as far as I know, it has been proved that you cannot reconcile that with any hidden variable theory unless it is non-local. But if it is non-local, we are back to square one. So nobody knows. Many companies keep investing on the quantum computer. They are seeing this happening all the time. If we want to put all our bank accounts, everything on quantum computers, promise it will not happen anytime soon. Because so far quantum computing seems to be very promising for calculation, but horrible for storage. And the reason is that the coherence will go down. So you will lose that information due to decoherence. That will be a completely different talk. So no worries, your social security number will not be going something like this. You might have two different social security numbers. One the IRS looks at you, so you might get to jail. Imagine a world which is really like this. So, if you were hoping for a solution of this, I don't have it. It's part of our job as quantum physicists to look into this and to see the connection with reality and the way we understand. My personal take-home message for all physics students is keep your mind open. Because it's very easy to get stuck in a mindset the way we have been looking at nature for many years or centuries. Well, maybe there is something we are missing. So this is still puzzling. Maybe some of you are entirely satisfied that this is the situation that we violate realism. Quantum theories are confused. But, so the most common idea is 1 century later, we are sort of scratching the surface of what. And I would like to close, this is a pretty famous quote by Albert Einstein, who like almost 1 century ago said, well, I'm certainly very respectful, but according to him, Einstein was very meditative. There is something that doesn't really add up here. I can't believe that all of that. And actually, I don't know if you ever heard of the EPR Einstein. I don't know. Oh, thank you. It wasn't something growing. That is a famous parallel. And it's sort of similar to this, although they were speaking about position and momentum, not about spins. But it's similar. So I leave you, so first of all, welcome to quantum physics. Thank you for your attention, and I leave you, inviting for question, I leave you to a picture of the which is always fun to look at. But thank you very much.
Thanks for a fantastic talk, Ettore, and now we have time for questions.
Very good. So I love the idea of entanglement. I don't know if you've heard me tell people, I think there's only one electron in the whole universe. That's it. That's it. It's all talking.
Just one electron?
Yeah, that's it. That's it. Yeah.
You mean one electron or just one gigantic field?
Exactly.
Because one electron would be a bit scary for all our life, but one gigantic field of energy that sort of embeds everything.
That's right, because
That's Wheeler's idea.
yeah,
And
absolutely.
the idea is that it keeps going forward in time as an electron, and then keeps coming backwards in time as a positron. Because a
That was,
positron acts just like an electron going backwards.
yeah, Feynman would talked about this with Wheeler, and it was like some kind of joke they had with each other. I don't know how seriously they took it, but the idea was essentially just had one electron going back and forward in time, and that the reason all electrons look the same is because they work. There's one electron.
Yeah, but let's face it, guys, we look at electrons in different ways and we see different things.
Then how come different electrons can have different energies?
Well,
Well,
so it's the same electron, but at different points in time.
Exactly.
So, but I don't think, even Feynman didn't take it seriously. I mean, it was
But
kind of like a
explain
joke.
entanglement, man. I mean, these entangled things across the universe.
Oh, wait.
I didn't really mention that word too much today because I didn't want to
I
entangle
know.
your minds too much.
So you
But
say,
this would be the physics of, and this mysterious entanglement, this was all about this presentation. It was all about entanglement. Because some ways to sort of make peace with it is people say, well, but it's really, as soon as you start sending the particles away, that entanglement would disappear. So when the particles reach Doug and me, those would be back to classical. And that would be wonderful if it agreed with experiments, which it does not.
Right.
Because they made very clean experiments where we got the entangled particles, and we see
That's my
this.
understanding, yeah, exactly. Even far distances and stuff, yeah, it's incredible.
So if you have one electron, you mean they are only present or only positive?
Ask Don.
Well, don't think of it.
That's
It's like a one particle thing, guy, you know, we think of an electron, we kind of draw it as a dot. That's not what the hell it is, right? Who knows what it is? So I just call it one electron, right? But it's all together, yeah. I mean, remember, all chemistry is all electrons, right, guys? That's what it is, yeah.
I see a few questions.
I think another thing to be added is some people believe that's not just depending, quantum mechanics doesn't depend on scale. It actually occurs at all scales, not just the microscopic, that it's at all scales. And I mean, we see the superconductivity is a large scale.
There you go.
But the actual system, the thing that they use in quantum computers are not microscopic.
Yeah.
Right?
They are just, well, the only one I'm pretty familiar with would be the superconducting one, and that is it's certainly the size of, I don't remember exactly, but far from microscopic. We are close to the millimeter range, you can still see the qubit effect.
Are you gonna do a talk on quantum computing? 'Cause
If
that
you
blows
guys-
my mind, I have no idea.
If you guys want to,
I'd love to.
I would do like on demand.
There you go.
I also wanted to maybe make a class or because that wouldn't really fit 1 hour. That's the problem.
I can imagine.
So I can do a cycle. That I can do. The point of quantum computing is that really to enjoy it, the people need to be pretty robust in linear algebra. Otherwise, it's a torture. Because it's all a linear algebra exercise. So I would put as a prerequisite that students pass a linear algebra class. Then I will be very happy to discuss quantum computing. I was just like the unofficial reviewer of a book of quantum information which will come out probably in a year or so. With two friends of mine, one is working at Rigetti in Berkeley, the other one is working at IBM in San Jose. And they are writing a book and they asked me if I could help because they wanted to become a book for universities. So I was their sort of unofficial reviewer.
Oh, very good.
And so I never thought, although all of you can go on the IBM machine and do the quantum experience, you can create an account and do a calculation on a quantum computer. That's not a fantasy, it's reality right now. Although, you wouldn't see the quantum computer in action, so you would actually write something Python-ish, press enter, and see a number. So you might close your eyes and know that the quantum, but I don't find it very illuminating. I never did it for myself.
So in classical mechanics we use phase space when doing statistical mechanics. Are you talking about the switch from phase space to Hilbert space for quantum statistical systems?
Yeah, it's exactly that. The phase space become, like in the mapping from classical to quantum, what is the phase space becomes the Hilbert space. All the observables in phase space becomes operators on the Hilbert space. And if you want to do the mapping very nice and cleanly, all the Poisson brackets become commutators.
Will you be
divided
covering
by
this
I
later
each part.
in our
So you are very well prepared now, thank you. But I will not change the grade of your video. You still need to pass.
So there is a supposedly IBM quantum computer.
Not supposedly it exists.
There is, yeah.
It's only that. So the key point is not about having or not having the quantum, because it exists. The point is that, are they really outperforming classical computer? Are the costs convenient? So what can you really do at the large scale level? That is the problem now. In terms of realizing it, it exists.
So I was told that that computer was a joke.
No, they're not a joke, it exists.
The storage is a problem, right? It's
But
working for that.
they would always use a classical computer as the storage part. Only the CPU
But the
would be
calculations
one. The
is-
calculation would be quantum. There are some algorithms for which quantum computer at the theoretical level seems to be definitely the winner. The initial hope was that all the exponential operators would become polynomial. That is clearly not happening. So that was a bit of a down. But there are some algorithms, the most famous, well, there is the famous RSCA, the password generation, the encrypting generation scheme that would be broken by the quantum computer. But that's essentially in the joke area. Although it's true that if they will have big quantum computers, all our passwords need to be regenerated. Because at that point, an hacker on a quantum computer might break into our... But yeah, it's a wonderful exercise in quantum physics. It's very promising. It still needs to it's still up to challenge if it will really become a big...
Right.
Because there are many conceptual. And all those things, for us, it's mostly like we enjoy an intellectual discussion. For them, this is a terrible headache. Because they need them to write the results of the... And entanglement is a huge thing. Yes?
So then what's the difference between the IBM, the quantum computer, and that? Mainland China, didn't they using optical system to create some quantum computation stuff?
Well, every company is, there are a few things, I don't know the detailed company by company, that I don't know. Because Google have their own, IBM have their own, Rigetti have their own, I know that there is one in China. They all compete. Normally there are three things that can differ from one to another. The first one is what is exactly the qubit for them. So the only one I'm pretty familiar with are the superconducting qubit. They use Josephson junctions to do the qubit. Other people, there are organic qubits, there are optical ones, electron spins in impurity electrons in material. That can be a difference. The second thing is how you implement one qubit gates. So how do you practically change one qubit into another? Take the state of one qubit into something else. Like on a quantum computer, you have 0 and 1, but you want something that allows you to go from 0 and 1 to maybe from 0 to 1 or from 1 to 0. So for quantum, it's crucial that you can go from any state to any other. So you have the X gate, Y gate, Hadamard gate, all the CNO. There are plenty. And the third one, and the crucial one, is how to do the 2 qubits gate. Because unfortunately, you cannot do all you need for computation with just transformations that act on a single qubit. Fortunately, you don't need anything that acts on n qubit. You just need 1 and 2. That's a theorem that you can prove. But the 2 is terribly hard, mostly due to entanglement. So how do you change 2 qubits together into something else that involves 2 of them? Each company has their own way to do that. And there are many problems there, like how to prepare the state of a qubit, how you measure the state of a qubit. And I show you that when you measure, you make a disaster.
Exactly, yeah.
So for a quantum computer, and also, as I told you, the property is not there until you measure, so you need to re-prepare it many times. And you cannot measure, just do it and keep measuring, because then it collapses. So you need a way that you generate it and measure, then you cancel everything, regenerate it and remeasure. It's a big deal. It's interesting though, it's fascinating. Yeah, I was thinking of maybe suggesting a topic course or something on what. But the point is that 3 units class is a bit too much for just approaching the topic altogether. Because I could, but that would be very heavy. On the other hand, 1 hour colloquium is ridiculously too short to say anything meaningful. So I remain open for suggestions.
Okay. Ettore, you're saying the 3-unit course is too much?
I think so, because so once you, well, it depends on how you organize it. You can even do a 7-unit course if you want, but then they would hate me. Because also, quantum computing, I see the knowledge of it in layers. In the sense that layer 1, the simplest, is really to understand the theory and everything. That would require probably a couple of units class. If you want to go all the way down to how really the quantum computer works, that is probably a program.
Yeah, pretty well.
Which would maybe need input from engineers and so on, because there are things.
Yes, exactly.
Although it's beautiful physics, because it's a lot of like electromagnetic waves in wires. There is the famous telegraphist equation that maybe some of you just bumped into at some point. So you have the propagation of electromagnetic waves in waveguides, which is something that normally in E&M classes, I don't know if you teach it, but in the 107 I skipped that.
It's in the textbook, and it's also in Jackson, but yeah, people usually skip it.
Yeah, so that would be the crucial one.
It's good to know if you want to design a radiation therapy machine, like a LINAC, because they use those. If you're going to accelerate electrons to megavoltage and to MeV energies and do it inside something this big, so there's a crossover with medical physics.
Well, definitely, there is a huge crossover. I
Yeah,
mentioned
they're always-
medical physics, and yes.
Yeah, you did.
Medical physics is all quantum. But biophysics has a lot of classical physics, but mostly because it's already tremendously hard at the classical level to do biophysics. Imagine if we want to squeeze quantum into there, we just, I don't know, maybe
There's an article that some animals use quantum mechanics for some orientation. There's some interesting scientific Americans. Yeah.
Was it like pigeons or?
Yeah, I forgot the details, but
Some
yeah.
kind of bird?
Some kind of quantum effect, yeah.
Wow. Yeah, there's so much we don't know.
I remember having conversations like this with people at conferences, and some people told me, okay, after you told me all this, my conclusion is that quantum is finally out of my life. So I will do research in classical, I will study fluids, the while other people say, oh wow, so quantum is the way to go because it combines philosophy with physics and...
Yeah, the ones that say wow, that's the ones you want as students, right?
Alrighty, so any other questions, comments? So if not, let's thank Dr. Vitali again. And if you want to come down and ask more questions,
I'll go with you.